In this video, we're going to start our study of the concept of cardinality. The cardinality of a set is a measure of a set's size. In particular, it measures the number of elements in the set. Later on, you might learn another way of measuring a set, but cardinality refers to the number of elements in the set. To find the cardinality of a finite set, we just need to count its elements. So if I have the set whose elements are just the letters A, B, C, and D, well, it has 4 elements, so its cardinality is 4. And we denote cardinality by card of A. So cardinality of A equals 4. If B is the set of all the integers between -5 and 5, including -5 and 5, if we count the elements in this set, we'll get 11. So the cardinality of this set B is just 11. So in this case, it is clear that the cardinality of A is strictly less than the cardinality of B. In general, also, if we have two finite sets, if we want to see if they have the same cardinality, well, the approach is actually quite simple. We have two sets A and B, they're both finite. Then what we do is we count the number of elements in A, we count the number of elements in B, and if those two numbers are equal, then we say that the cardinality of A is equal to the cardinality of B. This approach is very simple if we have finite sets that are not too large. But then this approach is absolutely useless if we have infinite sets, because we would never ever finish counting the elements in an infinite set. So we need a better way of defining what it means for two sets to have the same cardinality that will apply to infinite sets as well. So we say that two sets A and B have the same cardinality if there exists a projection between them, and then we say that the cardinality of A equals the cardinality of B. So what this is telling me is that if I have two sets and I want to determine whether they have the same cardinality or not, all I need to do is to find an injective function between the two sets. So if I have a set A and a set B, and I want to check that they have the same cardinality, I just need to find a bijective function from A to B. Now, there could be many different bijective functions that will take us from A to B. The important thing is that we need to find just one. As soon as we find a bijective function from A to B, we are done. We know that the two sets have the same cardinality, even though there could be many other bijective functions from A to B. Now, if there is impossible to find a bijection from A to B, then we say that the two sets have unequal cardinality. So, okay, cardinality of A is not equal to cardinality of B. Here in this example, we have two sets, A and B. A has letters A, B, C, and D, and the set B has numbers 1, 2, 3, and 4. So one bijection is the one that takes A to 1, B to 2, C to 3, and D to 4. But of course, I could have chosen a different bijection between these two sets that would also show that the two sets have the same cardinality. Now, when do we say that a set has a larger cardinality than another? Well, if we can find an injective function from A to B, then we say that the cardinality of A is less than or equal to the cardinality of B. If the cardinality of A is less than or equal to the cardinality of B, and the cardinality of A and B are different, then the cardinality of A is strictly less than the cardinality of B. This would happen, for example, in this picture, we can see that we can find an injective function from the set A to the set B, but it would be impossible to find a surjective function, right? So we cannot have a bijective function there. So that would be the problem here. You will see, well, the problem not, the situation here, because it's not really a problem, it's just that the cardinalities are not the same. So here we have the set with 4 elements, A, B, C, and D, and the set B has 5 elements, 1, 2, 3, 4, 5. Then it is quite easy to find an injective function from A to B. Here there is an example. but it would be impossible to find a bijection between these two sets. So in this case, we say that the cardinality of A is strictly less than the cardinality of B. Now we could have another situation, like in this case we have the set A has 5 elements, A, B, C, D, and E, and the set B has 4 elements, 1, 2, 3, and 4. In this case, we were actually able to find a surjective function from A to B, but it would be impossible for us to find an injective function from A to B, because remember that a very important part of the definition of a function is that every element in the domain, every input, has to have an output. So when we do that, we will be forced to have at least 2 elements in A that are mapped to the same output in the set B. Now, we can see in this case that, well, it's quite simple to see that we could find an injective function from B to A. Try to think about which one we can pick. So in this case, the cardinality of B is less than the cardinality of A. So these are the main ideas that you need to know in terms of cardinality and how we determine whether two sets have the same cardinality, or maybe that a set is smaller than another. So remember, the key part here in the definition is that two sets have the same cardinality if there is a bijective function between them. And we're going to take a look at how we can apply these to show that two infinite sets have the same cardinality. So, according to our definition, the cardinality of the set of natural numbers is equal to the cardinality of the set of integers. And here I've drawn at the top in pink we have the natural numbers, in blue we have the integers. So if I manage to define a bijective function from the naturals to the integers, then I will be proven that the two sets have the same cardinality. And here is how I'm going to do it. You see, I can send 0 to 0, 2 to 1, 4 to 2, 6 to 3, 8 to 4, 10 to 5, and then it would be 12 to 6. So for any natural number, I will map it to what? Well, first let's start with the even numbers. So if I have a natural number that happens to be even, I want to map it to the integer that turns out to be just half of that number. So if I have a natural number n that is an even number, I will map it to n over 2. And now what I need to do is, well, what should the output be for each odd natural number? Well, I will send 1 to -1. 3 is going to go to -2, 5 goes to -3, 7 goes to -4, 9 goes to -5, 11 would go to -6, and so on. So as you can see, each natural number is mapped to a different integer, and also each integer is the image of some natural number. So this function is injective and surjective, so it is bijective. Well, since we managed to find one bijection between these two sets, that immediately tells me that the two sets have the same cardinality. And here we can see how we can define this function that I just gave you in pictures. Well, we're defining the bijection from the naturals to the integers to be, well, for any natural number, n, we define it fn is n over 2 if n is even, and negative n plus 1 over 2 if n is odd. And now I will leave for you as an exercise to verify that, first of all, that these algebraic representation of the function agrees indeed with the picture I just gave you, and also to check carefully that this function is indeed both bijective and surjective. Here you can see that it could sound extremely weird to you that these two sets, the set of the naturals and the set of integers, have the same cardinality, because intuitively you might think that, well, the set of integers have all the natural numbers, which is all the positive integers plus 0, but it also has all the negative integers. So according to our intuition, then shouldn't the set of integers have twice as many elements as the set of natural numbers? It's weird, but according to definitions, because we were able to define a bijection between the naturals and the integers, these two sets have actually the same cardinality. That's why infinite sets are so weird and counterintuitive, because we could have a proper subset of an infinite set that has the same size as the bigger set. So that's it for our introduction to cardinality. In the next video, we're going to talk about the pigeonhole principle.